Good morning, everybody. Welcome to Science on Saturday. I'm Dr. Joanna Albala. I'm the Science Education Program Manager at Lawrence Livermore National Lab, and I'm so happy to have you here today to our third Science on Saturday series. And this year's theme is Computing the Future, where we're showcasing our innovative work using the power of computing from molecular biology to space exploration. So let's get started by welcoming our presenters today. Jeff Mirocha received a BS and a BA degree, both in geography and mathematics from Arizona State University, and an MS and PhD degrees in astrophysical, planetary, and atmospheric sciences as well, and has been at the lab for over 20 years. Adam Weiss is joining him today. He received a BS in mechanical engineering from Virginia Tech and an MS and PhD in civil and environmental engineering from the University of California, Berkeley. He is currently a postdoctoral researcher in the Atmospheric Science and Research Application Group at the lab. Joining them today is Ruiqing, who received a BS and MPhil in Building, Environment, and in Energy Engineering from Ruiqing University and a PhD in Urban, Climate, and Energy from the University of Hong Kong. And he is also a postdoctoral researcher at the laboratory. And joining our scientists today is Thi No, who received a BA and MA from the University of California, Davis. She is a life science teacher from Stockton, and she teaches biology at Capuchino High School in San Bruno. She is also a faculty scholar in the science education program at the laboratory. And let's remember to give our presenters our full, undivided attention for their talk entitled, Can Video Game Chips Make Cities Safer? How GPUs Help Scientists Combat Airborne Threats in Urban Areas. Now let's give them a warm welcome and let's get started.
Okay, welcome everybody. It's wonderful to see you. Thanks for spending part of your Saturday morning with us. So we're going to show a lot of cool results from some projects that we've been working on at the lab, but I think before we do that, we're going to do some brief introductions just so you know who we are that's talking to you today. So my name is Jeff Mirocha. I've been an atmospheric scientist at the lab for about 22 years, came here as a postdoc originally, and I did my graduate degrees at the University of Colorado in Boulder in astrophysical, planetary, and atmospheric sciences. And before that, I did my bachelor's degrees. I got concurrent degrees in math and geography at the Arizona State University. So I've always loved the weather. This is a picture of a really cool atmospheric phenomenon. This is called a shelf cloud. These are often seen in severe thunderstorms. And I loved meteorology. But after I got to the lab, I had the opportunity to start working on wind energy too, and you can see there are some wind turbines underneath this menacing cloud. And it was really fun to work on this project because the wind turbine engineers were building these wind turbines, but they didn't really understand the atmosphere very well and what kind of forces the atmosphere was going to subject these turbines to, like these giant storm clouds. So it was super fun to work across disciplines with engineers to better understand atmosphere, wind plant interactions, and all that cool stuff. I've also always loved science outreach. So this is not the first Science on Saturday I've ever done. Back in 2011, we did a Science on Saturday where we did wind turbine models on the little table over there where Tia is sitting. A few years later, I came back and did another one on renewable energy. And this is a fun slide because in the picture over there, you might notice somebody who you would recognize if you were at Las Positas College. That's Eric Harpel, who's an astronomy and physics professor here. So we had a lot of fun doing that. That's what I do kind of for a living, but I also like to do fun things too, so you might see me playing my bass guitar somewhere around town. Okay, that's enough about me. My role in this project is mainly as a manager and a technical advisor, but most of the really cool results that you're going to see today are due to our fabulous postdocs, the first of which is Adam Weiss.
Hello, everyone. My name's Adam, and I'm originally from Virginia. I went to Virginia Tech for my bachelor's degree, and then I moved out west to Berkeley to do my PhD. And like Jeff, I was also really interested in wind energy. The picture on the top right was a design project that I got to do while I was at college. And then on the top left, I'm actually on top of a wind turbine in Colorado. But then once I got to grad school, I was a little bit more interested in just the wind and the atmosphere itself. So I was able to do some fun field projects where I was installing some measurement devices to measure the wind, which you'll hear more about in this talk. And then that's me professionally, but then, I mean, who here likes Legos? Yes, I see a lot of hands being raised, right? You're never too old to keep building with Legos. So I have my own Lego city at home, and maybe you'll learn some things in this talk about cities that could relate to your own Lego city. So now I'll pass it on to Ruiqing.
Hello, everyone. My name is Ruiqing, and I'm the second-year postdoc researcher in the Lawrence Duval National Lab, and my research area focusing on the urban heat island effect and its modeling, and also the building energy consumption or the renewable energy system. I got my bachelor and master degree from the Chongqing University, and I got my PhD from the University of Hong Kong. So you may find me have a presentation in some academic conference, or you may also find me in some outdoor activities such as hiking and talking with the people over around the world. Yeah, next I will transfer to Jeff.
So that's us. Let's talk about what we're actually going to learn today. So we all live in cities. And on the flyer it says, how are video game chips, how is video game technology helping us make cities safer? Well, cities are wonderful places to live, but they also expose us to unique airborne threats. And when I say airborne threats, I mean things that can harm us from the atmosphere. So the first threat, maybe you guys have heard of urban heat islands, it's extreme heat. So cities can be cool in the winter, but often in the summer, and especially during heat waves, the built environment generates and retains a lot of heat and can subject the people living there to extreme heat stress, which, if prolonged, can lead to really negative health outcomes and stress for people. So we want to understand the nature of heat as a threat. A second threat that you might have noticed is contaminants or air pollution. There are lots of different sources of air pollution, and again, because of the density of emission sources and people living, large populations can be exposed to harmful air in urban areas. So we're going to look at these two threats. We're also going to look at models, because if we want to try to understand these threats and how to mitigate them or make them less severe, we use predictive models to help us understand these. Now, when most of you think of an atmospheric model or a weather model, you probably think of something like a global circulation model, which is here showing clouds moving across the landscape that is colored with temperature. These are large-scale global models. What we're going to talk about today is a much finer scale model that has just been built in the last couple of years that we're using to actually study the details of flow and contaminant dispersion and other things in between the buildings in these narrow street canyons that comprise the cities that we live in. But the most important, one of the really important underpinning technologies that enables us to do these really high resolution simulations of urban areas is the graphics processing unit, or the GPU, which, as you all know, probably already, has been used to render graphics in video games really rapidly, create realistic scenes. But we're now using the GPU in scientific computing to be able to perform the kinds of calculations that are required to do these simulations. In fact, the world's most powerful, fastest computer sits just a few miles down the road here, El Capitan, and it is built primarily of GPUs. So Richard is going to introduce the first of our threats, heat.
Thank you, Jeff. So before I start that, I want to ask everyone a question. When you live in the urban area, did you feel it's warmer in the urban area than the rural area? So it's, okay, thank you. So it's just a feeling or it's an existing phenomenon? Unfortunately, it's an existing phenomenon and it exists almost all over around the world. And a lot of scholars and scientists are studying on that. And we call that the urban heat island effect. There are so many reasons cause the urban heat island effect. For example, during the daytimes, the urban area and the rural area are under the effect of the solar radiations. However, in the rural area, the grounds will radiate back to the skies in the infrared radiation, so make it cooler. However, if you move to the urban areas, we have lots of buildings and we have deep street canyons, so the heat or radiation will be trapped in the street canyons or between the buildings. That makes the urban warmer than the rural areas. And another important reason is anthropogenic heat. That means the heat generated by the human activities, such as the vehicle we drive every day, and the heating or air conditionings on the roof, or machines in the factories. All these equipments emit the heat into the urban environments, and that makes the urban become warmer than the rural areas. So that's the daytime. So what happens at the night times? So when the sun goes down and the moon comes out, the only difference is there's no solar radiations, but the earth or the ground is still radiative back to the sky in the infrared radiation and make the rural area cool down. However, in the urban area, the heat or radiation is still trapped in the street canyons or trapped by the buildings. And also, we still have the vehicles or air conditioning working in the urban area that still emits the heat into the urban environments. And so that's the reasons the temperature profile or diagrams look quite the same overnight. Yeah, next we will have a demo to show that. Thank you.
Okay, so here we're going to do a little demonstration. On this side, we have a brick representing our urban area, and over here we have some wheatgrass representing our rural areas. We're going to use an infrared thermometer. Thank you, Adam. He's going to be our thermometer tech today. He's going to check the initial temperature of both areas, and I'll be recording the data.
All right, let's see. Looks like we've got 68 degrees if you're rounding up.
We got to round up.
Around 68 degrees for the brick. And then around the same 66 degrees for the grass.
Okay. All right. So let's see. We are going to use these heat lamps to simulate the sun during the day. We're going to let them run for about a minute. First, how about we make a prediction? After 1 minute, which one do you think will have warmed up faster? I want you to point over here if you think the urban area will warm up faster in 1 minute, or point over here if you think the rural area will warm up faster. Come on, place your votes. What do we think? I see a lot of, this way? Okay.
I'm seeing a lot of urban areas.
I see a lot of urban area. Let's find out. Has it been about a minute?
All right, I think it's pretty close to a minute.
Okay.
Well, let's see.
Let's see if
how
your
it's looking.
predictions are correct.
So, okay, it looks like the urban area is around 72 degrees, and the grassy area is around 73.
Okay. So the building material, the brick here, earlier Ruiqing mentioned, they tend to have a little more density, so they have a little bit of a higher heat capacity. So it's absorbing the heat, but slowly, but like a battery, it can kind of capture and store that heat. We're gonna check in the temperature one more time, and then we'll let it run through the day.
Yeah, and one thing to mention about the grass is if you're taking the temperature at the top of the grass, it's going to be a lot warmer than if you're deeper down inside the grass. And the reason is maybe you're sitting at a park and you're shaded, you're under a tree, right? It's going to feel a lot cooler there than if you're outside of where the tree shadow is and you're just on the grass itself. So, all right, I think it's been about 2 minutes now. Let's see what temperatures we're getting. All right, The brick is about 75 degrees.
Okay.
And the grass is about 74, 75 degrees. So let's say 74.
Okay. All right. We're going to let it run through the day a little bit longer, and then we'll check back in after Jeff speaks. Okay.
We'll be back in a few minutes to take a look at what happens later in the afternoon. We're going to use like 1 minute to represent more or less an hour. If you do really careful dimensional analysis, you can figure out that's the time scale. Okay. So how long have we known about urban heat islands? It turns out we've actually known about this phenomenon for almost 200 years. The very first study of urban heat islands was done in London. So you've all heard of London. London is a giant metropolis today, but back in the 1800s, it was a very small town, only a few kilometers across. But even back then, the first sort of citizen scientists were discovering that it was cooler in the countryside than it was in the urban core. So when we look at urban heat islands today, we can use much higher resolution imaging. So this is a really cool map of surface temperature, and this comes from an instrument on the International Space Station. This is a NASA instrument called EcoStress. So file this away for the future, but a good way to get funding is to have a really cool acronym. Okay? So EcoStress stands for Ecosystem Spaceborne Thermal Radiometer Experiment on Space Station. So spaceborne means it's in space, thermal means it's looking at heat, and radiometer is the instrument that we use to measure radiation. So in the slide that Richard shows, when the Earth is cooling to space, it sends out infrared radiation. But the wavelength of that infrared radiation depends on the temperature of the surface that's emitting. So if the satellite can detect that, or the spaceborne instrument, it can map surface temperature based on that radiation. So what you're seeing here is an image of the greater London area. This blue inset here is actually the greater, larger perimeter. So the original urban core was just in that black spot in the middle. These little black highlights pop out, and they show you what things look like visibly, and then what those same things look like from the radiation, so you can see their temperature. So if you look at the airport in the upper left, visually you can see lots of concrete. On the right, you see how much hotter that concrete is. So this is a heat map. The colors here show temperatures, with the yellow colors indicating about 150 degrees Fahrenheit, so that's pretty hot to the touch, and the darker colors showing cooler temperatures, about 60 degrees. So we can see in a lot of detail now how the urban heat island is. It's not homogeneous, right? There are parts that are hotter than cooler, but the urban core really is the hottest part of this map. So England isn't the only place where this happens. This is a scene from a rural area surrounding New Delhi, India. So we're now able to see that not only can the spaceborne instrument capture the heat island of the edge of Delhi, but you can actually see smaller towns and cities. So it's not just the big megacities that have heat islands. Smaller towns and cities have those as well. There's an area near us that has a pretty famous heat island, and that is Los Angeles. And what we're going to show here is that these heat islands actually persist overnight. And you can see that from the spaceborne radiometer instrument. So this is during the middle of the day. We have a different color bar here, but the red colors are the hottest colors, about 140 Fahrenheit, so still pretty hot. The blue colors are cooler. And in the middle of the afternoon, the battery is charged up. The urban areas have stored solar radiation, and they're really hot. So let's see what happens a few hours later at about 9:30 at night after the sun has gone down. And we notice you can now start to see where the more built part of the urban environment is still quite a bit warmer. Everything is cooling down a little bit, but the rural areas are cooling down faster. If we go later in the night, we notice that the urban area is still warmer than the rural area. And this persists through the whole night because, again, energy is stored during the day, and it's released back into the atmosphere at night. Finally, if we go to right before sunup the next day, we notice that the urban area is still warmer. And this is really important because what really causes the medical stress of heat isn't so much short exposure to high temperatures during the day. It's the fact that people can't cool down at night, especially if you don't have heating and air conditioning. And you can imagine if you watch this video for the next day, now the urban area is starting out even warmer, and so it just magnifies. So we're going to check back in here with our demo and see if we see the same thing in the demo that we see in the simulations.
Okay, so for our simulation, if we say about a minute is maybe about an hour during the day, let's say it's about late afternoon now that we've been letting it heat up. We're gonna do a prediction now. It's been 8 minutes. Earlier, they were about the same temperature. Now, let's make a prediction. Point this way if you think the urban area is warmer, or this way if you think the rural area. Or if you think they're the same, go like this. Oh, I actually see a couple of, but I see a lot of this. Okay, all right. Let's find out. Oh, we got one or two. Okay.
All right, this brick is looking pretty warm. I'm seeing around 80 degrees Fahrenheit. And let's see what this grass is saying. It's saying only about 75 degrees.
Oh. Okay. All right. So it looks like the heat that it's been absorbing all day versus the plants, they're able to lose a bit of moisture or transpire. So this creates almost an evaporative cooling effect. So we'll say sun has set now, and we're entering into evening time. We'll let the city cool down a little bit, and we'll check back in a few minutes.
All right, so we have spaceborne observations, we have demos. How do we represent urban areas and this heat effect in Earth system models? So again, this is an observation. Now this observation has a certain resolution, which kind of means what is the distance over which you can detect a change on the landscape? How clearly can you see an image? It turns out for this instrument, it has a resolution, a spatial resolution of about 100 meters on each side. So if you like to think in feet like we do in the United States, about 60 feet on a side. So we can differentiate a landscape change of about 60 meters, but nothing smaller. Okay, this is a pretty small area compared to an Earth system model that, let's say, covers the entire globe. So like a weather forecast model or a climate simulator. Even the highest resolution versions of these that are routinely used have a resolution of about 4,000 meters. So much coarser resolution. They see differences over a few kilometers rather than 100 meters. So what's relevant here is what is the spatial scale of a city or an urban core? Well, back of the envelope for a mid-sized town, a typical city might have about 10 kilometers across the most urbanized built part of the city, or about 6 miles. So when EcoStress looks down at this scene, it's able to differentiate variability where all these blue dots, blue markers are. So it can see even down to individual large buildings and patches of grass. However, the Earth system model uses a much larger footprint. It can't see that level of detail. It can only see differences occurring over 4 kilometers. So all of the variability beneath that resolution is what we call a subgrid scale process. It's below the grid that the model uses to solve the equations. So we have to use what we call an aggregated representation of the urban effects on the weather and climate variables we care about. And Richard is going to talk to you about how that all works.
Thank you, Jeff. So next, I will introduce how we simulate or calculate the temperature in a large regions. As we mentioned that the urban heat islands effect is a global phenomenon. That means it exists almost in each cities. And here we use Boston, which is a famous city in the northeast of the US as example. And if we look into the large regions around the Boston, it includes the Boston and Providence as a large cities. And it also includes some smaller cities surrounding the Boston. So if we want to calculate the temperature in so large regions, we can't resolve each single building in this area because that will make the calculation very expensive. So what we did is we divided the whole domain or the whole regions into different model grades with a grid spacing or resolution of 1 kilometer or 300 meters. And next, we will give each model grade a land-use land cover type according to their average physical characteristic, such as the average building height, average thermal properties, and average urban morphology parameters. For example, here, you may find some dark red regions or orange regions. That means the urban landscape types. And also surrounding the Boston, we have some green or yellow areas. That means the suburban or rural areas surrounding Boston. So from the picture on the left, you can tell where is the central urban area of the Boston and where is the suburban or rural area surrounding Boston. And if we look into the animations on the right, you may find this is a 24-hour diurnal cycle of the temperature pattern. That means it's a spatial distribution of the temperature hour by hour in 1 day. And if you look into that, you may find in the central area of the Boston, there is always higher temperature or it's warmer than the surrounding rural area or suburban area. That's the reason why we call that the urban heat island effect. And also, if you comparing the temperature patterns between on the right and also the landscape and land-use land cover map on the left, you may find the two patterns closely match with each other. Especially, we will represent some small urban heat island effects in the smaller cities surrounding Boston. So that's the way we simulate or calculate the temperature in the large regions. Next, we will also go back to the demos. Yeah.
Okay, so to recap, at the start, the initial temperatures were about the same for both. After about 2 minutes, they were about the same, and about 8 minutes in, the urban area was much warmer than the rural area. So now it's been nighttime for a little bit. One last prediction here, if you've been paying attention to our satellite data, now that it's nighttime, which one would have cooled off faster? Which one would be cooler now? You sure? Okay, let's find out. I see a lot. Let's find out if your prediction matches our satellite data.
All right, for the city, I'm seeing that the temperature is around 74 degrees. So it's cooled down a little bit, but not that much. Let's see the grassy area. Ooh, I'm seeing 68 degrees.
All right, so the brick or the urban area, since it absorbs so much heat during the day, and now it's slowly releasing that heat even into the evening. This is probably something you've experienced, you know, like walking around in a park in the evening, it might feel a little bit cooler versus if you're in the city, the temperature may feel the same, not as cold as if you were out in like a field. So that is our demonstration, a simple demonstration on how urban heat islands are formed.
All right, thanks for the great demo. So that's our discussion of heat. Next, we're going to talk about contaminants. And Adam's going to lead this discussion.
All right. Thank you, Jeff, Ruiqing, and T for kind of introducing the first threat, which is heat. But now I'll talk about the second ever-present threat, which are contaminants. And you've probably all experienced these before. The most obvious one is something that we tend to experience in California in the fall, which is smoke from wildfires, right? Those are contaminants. We generally don't want to be breathing that air. But then cities themselves have a lot of other mechanisms for generating emissions or contaminants. And those can range from things like cars or diesel trucks, right? There are fumes coming out of the tailpipe from those machines. And then also on the right there, you can see industrial processes, right? These things are spewing contaminants into the air. And then also being in a city, you're especially susceptible to what we call acute releases. So when there are things like accidents, chemical spills, fires, and what we're doing here is trying to really understand the threat of contaminants itself, how they are moving in and around a city. So Richard did a nice job of introducing this schematic for the urban heat island, right? We have warmer temperatures in the city compared to the rural area, but what if this, instead of this anthropogenic heat, right, the human-caused heat, we now have anthropogenic emissions. So human-caused emissions ranging from, like I mentioned, a chemical spill or a fire, or you'll hear me talk about this diesel truck example. So fumes coming out of a diesel truck. So instead of trapped heat, we now have trapped emissions, because the buildings themselves block the wind, or they channel the wind into certain streets, and they can directly affect how these emissions or contaminants are moving in and around the city. So instead of this relative temperature profile where you have increased temperature in your city, you have a relative contaminant profile where cities tend to have higher levels of contaminants themselves. And again, this example of our truck, our diesel truck, it's spewing fumes from its exhaust, and as a result, you have a plume. You're going to see a lot of videos of plumes during this presentation, and this plume is traveling around the city, and our job at Livermore is to understand the characteristics of this plume in order to better inform the public for public safety. So how can labs like Livermore help? So the first thing that we can do is get better measurements and better observations. So the labs are involved in these projects called Urban Integrated Field Laboratories, where they've gone to major cities, Baltimore, Chicago, Houston, and Phoenix. And in these cities, they've placed measurement devices to measure how fast the wind is blowing, where it's coming from. They've also trying to measure things like heat in different areas and at different times of the day. And then I just wanted to highlight one sort of measurement device that maybe you're familiar with but don't even realize it. So who here has ridden in a Waymo or an autonomous vehicle in the city? I'm seeing a decent number of hands. And they have these spinning things on the top of the car, and they're called LiDARs. And they measure how far buildings are from them or how far people are so that they can drive safely. And we use that same technology in atmospheric science to measure how fast the wind is blowing. I'll talk about a few more devices that we use later on, but now I'll pass it on to Jeff, who will talk about the second thing that labs are doing.
Right, so all science is founded on observations, but then we create models. And models help us codify our understanding, make predictions, and sometimes be able to peer in and find greater detail in the subject that we're studying, so we love models. Again, when most of you think of an atmosphere model, you probably think of something like a weather prediction model or a climate simulator. In fact, Livermore Lab leads the development of the Department of Energy's new Energy Exascale Earth System model, which is the newest, fastest global simulator in existence. And we're going to talk about what exascale means in a minute. We learned that you can represent things like urban heat islands in these models, but you have to use an aggregated representation because the model resolution, even in these really sophisticated high-resolution models, are still too coarse to represent all of the details that are happening in between the buildings. But what if we could actually resolve all of these processes? Well, it turns out we can, thanks to two things. One is a newer, faster model. So we're going to spend most of the rest of this talk discussing a new energy model called the Energy Research and Forecasting Model, which is a model that's been developed over the last few years, where you can actually simulate the flow in between the buildings and better understand how urban environments interact with things like heat and contaminants. But in order to have this new model we needed the underlying computational support provided by the graphics processing unit, which is the only way that we can run these simulations fast enough over big enough domains to actually find answers that we care about. So why is the GPU so important? Why are these high-resolution simulations so expensive? So I want to give you a little overview of just how Earth system models work in general, so you can see the power of the GPU. So what is an Earth system model? It's a bunch of equations. We're not going to go through these equations. There isn't going to be a test. But I just want you to understand that fundamentally, we have a bunch of equations that need to get solved. What do these equations represent? Well, they represent physical things in the environment that we care about. So each of these equations sort of maps onto a picture of one of these processes. So in the real Earth system, you have lots of different systems. You have the sun that's bringing in energy. You've got the Earth radiating energy back away. You've got clouds at different heights. Some of them are raining, some of them aren't. They're shading the surface. They're causing rain. You've got the surface at the bottom interacting. You've got water. You've got land. You've got forest. And then the thing that we really care about is that you've got this city in the middle. And this city has its own characteristics of how it warms up and cools down and how contaminants are generated and move through that landscape. So we have to solve these equations here over and over and over again, which makes this a huge computational challenge. So these huge Earth system models are among, I think, the crowning achievements of human legacy. They're amazingly complex, and we can actually use them to do things like predicting the weather and understand lots and lots of processes. Well, we don't actually solve these equations, because if you've had a little bit of math, you'll see these are nonlinear partial differential equations. They're too complicated to solve. Nobody can solve them, not even the best mathematicians in the world. But what we can do is we can write computer code that can take these equations apart and approximate their solution. So when you see people coding, they're often writing code that can solve equations like this. And in the example of the code, this is actually a snippet from our Earth model where you're seeing that we're calling a GPU device. And that's a hint at how we're going to use the GPU to solve this problem. So how do we solve this problem? Well, mathematical equations are continuous, but we use discrete representations. We use a model grid. We don't solve the equations everywhere, but we solve the equations on a select set of grid points. So the red circle here shows the middle of a grid cell. We divide the horizontal grid and the vertical grid, and we usually index those with a letter like I, J, and K. Those are pretty standard. So these are all integers, and they specify the locations of these grid points in three-dimensional space. So I might indicate moving along in the east-west direction, J, the north-south direction, and then K, the vertical direction. So just like in a Cartesian coordinate system, if I give you x, y, z, you can plot that in three-dimensional space. In model space, where the computer is managing memory, it keeps track of the integers that specify the locations of these grid cells. And that's how it's able to solve these equations. So a model has a resolution, right, as we described earlier, the spacing between the solution points. So the size of a grid cell. We denote that delta x. What do you suppose determines delta x? Well, there's two things. One is the area you want to cover. If you're covering the whole planet and you don't have that many grid points to use, you have to space them pretty far apart to get around the whole thing. Whereas if you're looking at a smaller area, you might think, oh, I can put things closer together. But the other factor is our computational ability. How many grid cells can you solve with your computer? If you have a slow, weak computer, you can't do that many computations, right? So that limits your grid size. So these are related. So for a little context, let's go back to sort of the dawn of modern global simulation, where we started using global weather models a lot in scenario planning and weather forecasting. Just 25 years ago, about the maximum number of computations we could do over the globe was about 10 million. We could use about 10 million grid cells. Now, it sounds like a lot. It is a lot of grid cells. Turns out, if you want to divide it up into horizontal and vertical directions, it's about 400 grid points in each direction and about 60 in the vertical. That's what these models tend to use. Well, let's figure out what the grid spacing is, because that's the number of grid points, but that's not a physical dimension. If you look at the Earth's circumference at the equator, it's about 40,000 kilometers. You can look it up, 25,000 miles. So if you want to divide that area, that length, by 400 grid points that you have available, that gives you a resolution of about 100 kilometers, or about 60 miles. So if you wanted to look at just California in one of these sort of coarse scale global models, you might notice there's not a lot of detail that's resolved here. It can't see differences in terrain or differences in land cover at a very fine spatial scale. This model can tell you how the large scale weather is evolving, but it can't give you much detail at the local scale. Well, fortunately, in the last 25 years, we've come a long way. We've increased the amount of computation we can do by about a factor of 1,000, right? We're up to 10 billion grid cells now that we can solve. So what that means is we can use about 10,000 grid cells instead of 400 in each of the horizontal directions, a little bit more in the vertical direction. So what kind of resolution can we get now that we have that many more grid points that we can use? Well, if you take that same distance, the circumference of the Earth's at the equator, and divide by 10,000, you get about 4 kilometers or 2.5 miles. So modern global simulators or weather prediction models now use a mesh or a grid that's fine enough that you can resolve some of the small scale details. Like if you want to know where it's going to snow in California, it's nice to have the mountains actually represented in your domain. Or if you know where it's going to be hot, that you actually have the Central Valley as a big bowl in the middle of California. And the new models can see that. So this is really cool. This is climate, weather, large scale, global. And 4 kilometer is pretty good, adequate for most of the things that we would want to do, like weather prediction and stuff like that. But do you think it's enough to resolve individual buildings? Not even close, right? So what delta x do you need to actually resolve a city? There's a rule of thumb that we use that any object or structure needs about 5 or 6 grid points in order for the solution to really be aware of it and represent it correctly. So I'm going to call that a structure. A structure could be a building, or it could be a canyon, a street canyon between the buildings. So by our rule of thumb, pick a building size. If you want to resolve your house, you probably don't care about your house, but you might care about larger buildings like warehouses, buildings in downtown. So you might take a building like the size of this auditorium. Let's say that's 100 feet or something like that, which is about 30 meters. Okay, so you need 6 grid cells. And if you want to resolve the street that's next to it, where the flow might channel between the buildings, you need about 6 grid cells. If you take 30 meters and divide it by 6, you get 5. Everyone can do that. So in order to represent an urban area with some level of fidelity, you really need grid spacing around 5 meters, which is about 16 feet. Much, much finer resolution than you need for a weather simulation model. So given that you only can space the grid out 5 meters at a time, how large an area can you model if you're only using 5-meter grid spacing? Well, if we remember, we have 10 billion grid points. That's what the fastest computers can do today. And if you remember, that's 10,000 in each horizontal direction. 10,000, if we take our 5 meters and multiply it by 10,000s, it means the biggest simulation domain we can really do is about 50 kilometers or 30 miles. So that's not very big. You'd barely see it on a map like this. And in fact, we're sitting here in Livermore, and if we put this 10 billion grid 5-meter domain over downtown San Francisco, it wouldn't even reach all the way out to us. So urban simulations are very demanding in terms of the amount of computations you need to do to represent the fine-scale structures. But it gets even better, because finer resolution means you have to take a smaller time step. So what is a time step? Well, we have all these equations. They're time-dependent equations. If we want to do a simulation for what the weather's going to be like tomorrow, we can't just get there in one jump. We have to take small steps forward in order to keep our numerical methods that we use to solve the equations stable. So this model time step is what you use to advance the solution in time. Well, how big a time step can we take? Well, of course, it depends, right? It depends on the resolution. And here's why. So the reason you need to take a small time step is because you can't have information moving across several grid cells. The code will blow up. Doesn't know what to do with that. You can go part of the distance across one of these grid cells, like one of these squares on the left. You can go halfway across that distance and then recalculate all the equations. That's the time step in order to keep the numerical solution stable. So if we think about 100 kilometers, well, what is the fastest that information can go in the atmosphere? What is the fastest wind you can think of? What kind of thing? Well, lightning's not a wind. Good try. That's faster. But like hurricanes, tornadoes, jet streams, if we use a characteristic velocity or a representative wind speed of 100 meters per second, we can do some simple math. If you remember distance equals rate times time, you can divide distance by rate and get the time it takes for flow to go from left to right across one of these grid cells. You divide that by 2, and it turns out, trust me on the math, you can take a time step of about 500 seconds. That's how often you have to stop and solve all of those equations. Now, that doesn't seem so bad. That's about, what, 8.5 minutes? So if you want to do a day, it takes you about 173 of these time steps. So an older, slower computer can chunk through those calculations. But if you come over here, because the domain now, the grid cell is only 4 kilometers instead of 100, and you redo the math, you can only take a 20-second time step. So you have to stop every 20 seconds, recalculate all the equations. So it takes you about 4,000 iterations, as opposed to only 173. Okay? So this is getting more expensive, right? Because you have to do many more calculations to get to a day. Suppose we go to our urban area. Well, because we're only using a 5-meter grid spacing and you still have to obey that rule, you have to use a really small time step, and it takes millions of calculations. So urban areas are incredibly challenging for us to model explicitly, or where we're resolving the buildings, because they require many, many grid points, which means you have to solve all those equations at many, many points in the domain, and you have to do it very, very many more times than you do for a coarser scale model. So we need a more powerful computer. And that's where the graphics processing unit is coming in. This is really needed for cities. And Adam is going to explain why.
So Jeff mentioned that we need GPUs, but let's quickly understand like why or like how they work. And well, to start with, let's talk about a CPU, or a central processing unit. And you probably have all used one of these and don't even realize it, but they're in your usual laptops, and they're really good at doing a wide array or a diverse range of tasks, things like web browsing, email, but it does all these things sequentially, so one after another, which makes it not very fast. GPUs, on the other hand, were designed originally for video games. They were designed for a single purpose, and in order to render the graphics for video games, it does all these tasks in parallel. So it's much more efficient, and it's able to do a lot of things at the same time. And by leveraging that technology, we're able to bring it into our codes, making them a lot faster. So just to further hammer home the importance of GPUs, Jeff mentioned the world's fastest supercomputer, El Capitan, is just a few miles away from here in Livermore, and it's filled with GPUs. It actually has over 40,000 GPUs, and it's what we call an exascale computer. And does anyone know what the prefix exa means? It's like million, billion, trillion. It's past that. Not seeing many hands. It's 10 to the 18th, or 1 followed by 18 zeros. And it's able to do that many calculations per second. So it's extremely fast. And to put that into context, this is an older model that we have that was designed for a CPU machine. And we were really happy with this maybe 5, 6 years ago. And it's a 500 meter by 500 meter square footprint of Oklahoma City. And you're able to directly represent turbulent, gusty winds, as well as the red thing, which is like a scalar, or it could be, I guess, fumes from a diesel truck. Let's say that's what it is. And this is kind of a small area with the CPUs, but then now with our new GPU machine, the red box there, this is the same setup for Oklahoma City. The red box represents what the previous generation of tools with CPUs could do. So with GPUs, we're able to simulate a much larger area. We get a more accurate representation of the plume. And then we're also able to see all these other really cool things. Like in the back, the cross-section is the wind. So normally when you're standing on the street, you can feel the wind, but you can't really see the wind higher up. But it tends to be a lot faster up there, and that's what the yellow colors represent. And then closer to the ground, you see a lot more blue, which are slower wind speeds. So then this is our latest and greatest simulation, which I made especially for you guys. It's a 15-kilometer by 15-kilometer area, and that red box represents the old little area we did before, and you can actually fit close to 1,000 of those red boxes in this area. So what you're looking at here is mostly wind speed. A lot of the blue represents slower wind speeds, and you can see these really tall buildings in the downtown area, and they really slow the wind. And then another thing I want you to notice is maybe in more open areas where there aren't as many buildings, you see a lot of yellow. So you see a lot of faster wind speeds. Even maybe areas where there are interstates or wider streets, you have faster winds. But then in the more narrow streets, you have a lot slower winds. And understanding how the wind behaves in this urban environment is, again, important for helping us understand how threats are moving in and around cities. So things like contaminants or heat. So that visualization is really cool, but how do we know it's actually good? How do we know it's predicting what we want? And well, we need to compare the model predictions with observations. So I'll dig further into this Oklahoma City case where researchers from the lab placed all these measurement devices in these, where these magenta dots here are. So we're looking at a top-down view or a map of Oklahoma City. Each magenta is a measurement device. And I mentioned one before, LiDAR. Another one you've probably seen, sometimes these are located on the tops of poles on highways, is a wind vane. And it measures how fast the wind is blowing and what direction it's coming from. And then a little bit more complicated, this one is called a gas bag analyzer. And that cardboard box in the top left essentially captures the air, and then it tells us how much gas is in each air. So now we're looking at our model, our video game type city. All the magenta dots are our measurement devices. And then we run this simulation. And we have this plume, which represents gas or fumes coming out of a diesel truck. In this experiment, it was an inert or non-reactive gas. And that's what our model predicted. So if we want to compare it with observations, right, our researcher placed all these boxes around Oklahoma City. And now we can fill those magenta dots in with how much gas they measured. So red represents more gas, yellow represents less gas. And then we can see where the gas was released from, this pink star. And downwind of the pink star, you tend to see more red. And then as you go further away, you see yellow. And we want to make sure that is what our model is predicting. So let's compare. It looks pretty good, I think. We're seeing a lot of reds where we'd expect and a lot of yellows. All of this is overlapping with the measurements. And the other really cool and important thing by having our models is we're able to fill in the gaps between all of the measurement devices, right? It's not possible for our researcher to place a large number of measurement devices in every single spot. So we need to use models to supplement them to better understand how contaminants or other threats are traveling in and around an urban area in order to better inform the public, which Jeff will talk about next.
All right, thanks, Adam. Those are pretty amazing simulations, don't you think? I mean, if you've been doing this for a while, they're pretty mind-blowing. So why does the lab care about airborne contaminants and urban heat island issues? Well, one of the reasons is we have a lot of missions at the laboratory. We do lots of different things, and one of the things we do is provide decision support in the event of an airborne release of contaminants into the atmosphere. We have, for 45 years now, been the home to a center called the National Atmospheric Release Advisory Center, which is our 24/7 emergency response program that is staffed with people, and we use computers to generate plots to provide first responders and the public guidance on what the best thing to do is if there's ever a high pollution event. And so this product on the left that you're seeing represents one of these sort of fast-running decision support tools that the lab can basically press a button and generate in a matter of seconds or minutes. But what goes into these are the higher fidelity, higher resolution models that can resolve these processes. The last generation of decision support tools, like the one on the left, were informed by the last generation of simulation tools like Adam showed at the beginning, the little box with a little bit of Oklahoma City, which is great. It's what we could do at the time. But now we can do these kinds of calculations, which are going to give us a much better ability to both understand and predict what's going on in urban areas so that we can help keep the public living in city areas safe. And I will add that as the Earth model continues to develop, like adding heat down into the urban scale, we haven't done that yet, we're working on that, but we're going to do lots of other things with this model that are going to be mind-blowing. They're going to push the science forward, all enabled by the GPU. And hopefully we'll get to come back here in another year or two and present some really new cutting-edge results from the use of this model. So for the rest of this presentation, let's do a summary and figure out what we learned, and I'll try to leave also with some remarks about science and how we do science in the modern world. So we learned that there are threats to people living in cities. One of those threats is extreme heat. And this is only going to get worse in the future as urban areas get larger and use more energy. Think data centers, right? We're always using more energy, and that energy creates heat. And then there's contaminants. As cities get larger, there are more emissions, but there are also more places where contaminants can get trapped, and more people that we have to protect. And then there is the underlying computational support provided by the graphics processing unit, developed for video games. So we started out by saying, can video game technology make cities safer? And now hopefully you see the connection about how the problems we need to solve are so big that we need a next generation of accelerated computers, and the GPU provides us that capability. There's a second thing I want to spend a couple minutes talking about that was kind of implicit. So it's what we learned, but I want to make sure we all understand this. If you think of a scientist, back in the day, somebody sitting alone at their desk, scratching their head, going through pencils and paper, trying to figure something out, and then finally they get it, and they run out into the streets, scream Eureka, and they're famous, and the world loves them, right? And they spend the rest of their life in glory. But that's really not how most science gets done today. It's very collaborative and very complementary. So for example, in the work that we're presenting today, there are the scientists. We come up with theories. So we say, why do we think urban areas are warmer? What might be going on? So we go out and we observe it, and we think about what the observations tell us, and we put together mental models of what's going on. But we rely a lot on mathematicians to help us cast our theories into a mathematical framework that makes sense so that we can build models, conceptual models, and that we can develop also methods to solve these, because often these equations that we come up with are just too complicated to solve by pencil and paper. But we also like to build models that actually crunch the numbers and run code. So we need computer scientists. They help us with the codes and the algorithms so that we can solve all these equations to represent the physics. And then we can look at the results of that and learn something about it. And then, of course, there are engineers who build the things we care about, like the GPU, the computers we run, the cities we live in. And I want to mention, too, just one other sort of back-of-the-envelope way of thinking about what the GPU enables us to do. It's accelerated these atmospheric codes by about a factor of 100. Now, you might think a factor of 100, what does that really mean in everyday life? Well, 4 days is 96 hours, right? It's about 100 hours. So let's say in my CPU-based code, 5 years ago, I would go into work on Monday morning, I'd submit a job to run, and then I'd have to wait 100 hours. So I'd go to lunch, work on something else. Tuesday, I'd come in, I'd work on something else. Wednesday, I'd come in, I'd work on something else. Thursday, I'd come in, I'd work on something else. Friday morning, my code is done. Now I can look at the results. Now I can do that in 1 hour. I can send off a job, go get a coffee, come back, look at my results. It's really going to accelerate workflow massively in what we can learn. So don't be afraid of these technologies. They're not taking over. They're going to become your assistants. And this is an ecosystem, right? As we engineer more things, we need to do the science to understand their implications. We built these fabulous cities, but now they have threats. So how can we scientists examine that built environment? So it's always an interaction in these multidisciplinary teams. So this new model, the ERF model we talked about, it's not just developed by us, okay? I'm very proud to have been the original principal investigator that conceived this model and got the first funding for it. That was from the wind energy program back in DOE, but now we're using it for urban areas because the technology transfers. One discipline had a need. We need to bring the weather down to the wind plant scale. Now we have urban areas, and we want to understand how the urban areas interact. We have the basic framework to do this, but no one person can build a model like this. So even in this room, we have the project manager from Livermore. We have one of the computational scientists who runs the computational side of things. We've got people at other labs. It's a huge endeavor, but through huge endeavors, you can do really high-impact science. And the second thing I think is important is the people. You know, who are we and what do we bring to the table? I come from an atmosphere background. I love crazy weather, but I got to work on wind turbines. I don't really understand wind turbines all that well, but I know the atmosphere. But Adam came in, and he understands wind turbines really well. So if we want to make wind turbines work better, we need to come together and discuss the issues so we can work collaboratively to create a better wind turbine, a better wind plant, better energy production writ large. We can extend this to solar. We can extend this to tides. And then we wanted to go after the urban stuff, so we brought Ruiqing. So with that said, you know, we all have different skills and abilities, talents, passions. We're all different, but we're all important. We all have something to contribute. So I would leave you with a question: what unique skills and passions can you contribute to make the world a better place? Thank you.